Alright, so this is the second part of the CT physics talk, and this is going to be a talk that covers radiation dose and then CT artifacts. So let's talk about dose. So what effect does pitch have on dose? Remember that we said if we have a pitch less than 1, that means that our slices are overlapping. So if we have overlapping slices, we're going to have more dose. And the relationship is proportional. A pitch of 0.5 is going to double the dose. A pitch of 2 is going to cut the dose in half. It's the opposite. So 0.5 equals 2 times dose. My point is that it is proportional. So there's a variation with the scan plane. So in a regular diagnostic imaging setting, the entrance dose for the skin is much larger than the exit dose, because your low energy X-rays are going to be attenuated early on. In CT, it's different because the scanner spins all the way around and you've got a very highly filtered beam. So the dose is symmetrically distributed, or at least it's supposed to be. Now obviously the center is still going to end up getting less. Body phantoms show it that it's about half as much in the middle compared to the edges. So something like this. Now this is for something that has a large, the surface is very big, like the belly, for example. Now the head is smaller, so the central portion and the surface will end up being very similar. It's more homogeneous. So there's this concept of, or vocabulary word I should call it, called CTDI, or the CT dose index. Basically what this is a radiation dose that is normalized to the width of the beam. Now there's a couple different types of CTDI, more vocabulary words. Anytime you see something like that, then you realize that there's the other one is going to end up being a distractor for multiple choice. So a weighted CTDI, this is something that you think about with that belly, or the central third. You got third, central, 2/3 peripheral. And that added up gives you your weighted CTDI. It's correcting. Or you can have a volume CTDI, which is your weighted divided by your pitch. Now there's another vocabulary word that's probably even more important, called DLP, or dose length product, and you can imagine that this is going to involve the length of the scan, dose length product. So you take your volume CTDI and you multiply that by your scan length. So going back here, this one is your volume CTDI. So if you were going to start all the way at the beginning, you'd have to calculate, if potentially, a weighted CTDI to use in the calculation for your volume CTDI, to use in the calculation for your DLP. Now, what is the effective dose that you are actually, giving the patient? To calculate that, you need the DLP times a constant K, and this constant is variable depending on the body part. So what are the big differences between CTDI and DLP? CTDI is given in gray. It's usually milligray. DLP is given in sieverts. So what the hell is a milligray? What the hell is a sievert? How are they different? So this is a flow chart that it's in my book that I use to sort of distinguish between these things. So gray is a term for energy absorbed. It's a physical quantity. So this is your absorbed dose, or your radiation dose. It's basically the amount of energy absorbed per unit mass at a specific point. It's measured in gray, or rads, which is another unit. 100 rads is 1 gray. And this is how much energy from ionizing radiation has been absorbed in a small volume. Now you can multiply that times a radiation weighting factor. Weighting factor for X-rays and gamma rays is essentially 1, so it's a 1-to-1 relationship, and that's important. So in other words, 1 gray equals 1 sievert as long as you're using X-rays. Now, if you're using an alpha particle, like you're doing radiation ablation therapy, then you have to multiply it by like 20. It hits harder. It does more damage for this equivalent dose. So it's a correction that's made for the type of radiation that's being done. So these are essentially equal for the purpose of X-rays, including CT. Now, when you move all the way over here to tissue, or to effective dose, and that's usually the terminology that's used. That was a question, right? Effective dose. This takes into account whether or not the radiation has been absorbed by a specific tissue. In other words, you are taking into account the type of radiation, which you got from here, and the variable sensitivity of the organ, which you're getting from here. If all the dose is absorbed into the tissue, then 1 gray is still going to end up equaling 1 sievert. If you're dealing with organs or a specific body part, you have to use this tissue weighting conversion factor, which, you know, they have to give you that if they wanted you to do the math, or they could just ask you. The bottom line is the DLP is more of a biologic effect, whereas the CTDI is technically by the book like a physical quantity. It's the difference between gray and sievert. Sievert is for something that's alive. So the way I remember, it's like a biological thing. All right, so let's move on and blitz through these artifacts. So the first artifact is this idea of cupping. Now, if you remember this picture that I showed here on a prior slide, there's variation depending on the slice plane. Even though this is a head, and I said you usually don't see this kind of difference unless it's big, you can see it sometimes in heads or an artifact. So you've got X-rays passing through the middle of a uniform shape, like a head or a round belly, and the more hardened X-rays are going to be those, you know, they're hardened more when they travel through the middle relative to traveling through the periphery, which is, you know, a shorter path. And the harder the beam, the slower the rate of attenuation. So you're going to end up with the center of the image darker than you do the peripheral portions. If you just remember this sort of picture here, and that it's lighter in the middle, it didn't get enough juice there relative to this outside. Something like that. So here's our next one. Notice the patient's arms are down, and we've got these streaks, dark bands. Do a zoom in here. So when you see these dark streaks, this is a type of beam hardening. Basically, you see this when you've got two objects that are both dense, and X-rays pass through the first one are less attenuated than those that have to pass through both. So you end up with these dark bands and streaks. And you can fix this a bunch of different ways. You can pre-harden the beam to try to remove lower energy components. That would be like adding a bow tie filter. There's certain software that can be used, but probably the easiest way to fix things is to just position the patient correctly with their arms up, or tilt the gantry to avoid going through too dense things like that. So here's the next case. This is like 3 images stacked. I'm going to scroll. So here's a top image. Here's the middle one. Looks like a PE, right? And then here's the one underneath of it. It looks like there's just lung under there. So back in, middle, top, middle, below. So are you going to have to call that? Is that PE? So this is an idea of partial volume. So I said that data is acquired sort of in these voxels and these three-dimensional cubes. So if you've got information on a ball, a solid ball or nodule or piece of bone here, you know, it's right dead in the middle. It's gonna show up. But what if it is sort of half in one box and half in the other? Well, then you're gonna end up with something that looks like it's gray. Basically because it's averaging anything, all the information in this cube is getting averaged together, and then it's generating an image. So we've got this plus a bunch of darkness, and you end up with something that's like that. So how do you fix that? Basically, you make the slices thinner. And if the noise is really bad, then you can acquire thin slices and then do a post-processing correction and thicken them. But if you've got thinner slices, you are going to be able to just, it's going to go black, white, black, 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 instead of a gray in there. Alright, so hopefully this will project well. Just sort of have this sort of mottled, wavy, pixely looking stuff in the middle here. And this is a gigantic fat guy, right? So this is this concept of photon starvation, where it looks grainy. So your options to improve this are more photons, right? Improving the number of photons per box, increase the MA, or decrease the slice thickness. Increase the slice thickness, make the boxes thicker. So again, you're getting more photons per box. So the next case here is this metal catheter that's in the heart here, and it's showing these alternating streaky bands, and this is the so-called metallic streak artifact, and it's actually a combination of a bunch of different artifacts. It's beam hardening, there's partial volume averaging, different density ranges, much higher than what's expected by the computer. So the testable trivia is probably that metals with high Z's, like iron and platinum, tend to have more artifacts than things with low Z's, like titanium, like the more modern stuff. And you can fix it by increasing the KVP sometimes, or by using thinner slices instead of thicker slices. That reduces the partial volume effect. There's also certain hardware or software packages that do different data interpolation that can help reduce it. Alright, this is an idea of incomplete projection, where I've got this, I did a zoom up here. This fat guy's fat, is projecting outside the field of view. So if you've got parts of your body hanging outside the field of view, they're still attenuating X-rays, and it's messing the math up for the computer. So you end up with this sort of differences in density that you're seeing here all the way around. You're seeing it a little bit over here on this non-zoom portion as well. So to fix it, if you can reposition the patient, it's probably the only thing you can do. And now we've got this. This is like an Ant Mini artifact for CT. This is a ring artifact, and it's a calibration error or defective detector. It's very characteristic looking if you've seen it. And lastly, there's this idea of stair-step artifact, which is, these little stair steps here. And you see it on a multiplanar reformatted image if you've got if they're too thick, and you don't have overlapping intervals. It's actually less severe on a helical scanner relative to axial, but the way to handle it is to make thinner slices. So here's an example, same thing redone, this time with thinner slices, so you don't have those non-overlapping intervals anymore. Okay, that's pretty much the high points for CT artifacts.